Hey everybody, note that we could find a very crude upper bound for this trigonometric sum by just quickly noting, and this is crude, we're going to do better than the one I'm about to write down, but we know that cosine x and sine x, by their unit circle definitions, are less than or equal to 1 for all real x, right? That's just unit circle definitions. Now notice these numbers here are pretty close to 5. The square root of 23 is approximately 5. I'll put approximately 5 right here. And the same thing for square root of 24. It's approximately 5. And so just like that, we can see a very crude upper bound. And I'll just write UB would be 15. Right? Upper bound would be 15. And again, we're not necessarily trying to find the least upper bound. That would be nice. But an upper bound would be 15, right? So technically we're done with the problem, but let's go a little sharper than that. Now it turns out this thing is set up nicely for Cauchy Schwarz Inequality. You guys may have seen this. You can think of it as the square of the inner product of a couple of vectors is less than or equal to the product of the squares of the magnitudes of the two vectors individually. All right, so we're going to use that and done most of the work for you. Notice that these the root 23 and root 24 squared gives you 23 and 24 respectively here. Okay, that's this part right here. Okay, and then 5 squared is certainly 25, right? Okay, now we end up with cosine squared plus sine squared. Of course, we have that well-known result that's you see over and over on a problem like this: cosine squared x plus sine squared x is equal to 1. The Pythagorean Identity, which is what gets used, that's where this 1 comes from. Okay, and then this cosine squared is here, so cosine squared plus sine squared is equal to 1, which is this 1 right here. Now what I did, folks, is I put down, I said that this could have a maximum value of 1, right? So that's where the 2 times the 72 came from. But notice that cosine of 2 pi on the unit circle is just 1, right? That's equal to 1. But what makes this kind of a concern, I guess, if you want to call it that, sine of 2 pi is 0. Just thinking of the unit circle definitions. Okay, so you can see that doesn't fit in very nicely with a maximum value, right? Because that would make this term equal to 0. But we're just looking for an upper bound, all right? And so this is true, okay? And so this would be equal to, this would be equal to 12. And we have found an upper bound. Now I'm guessing there's some other types of trigonometry that I'm unfamiliar with might make this simpler, you know. And also notice we never would have equality here. Not that it's particularly important, but notice for equality to occur, 23 over cosine x, we'd have to find an x, square root of 23, square root of 23 over cosine x would have to equal the square root of 24 over cosine x. Okay, the ratios of the terms, I guess, or the coordinates, whatever you want to call it, have to be equal, and that already fails just for the first 2. We don't even have to write down 5 over sine x, because if you think about this, these are just the graphs of the secant function. Okay, and so there's no way that there's no solution in this, no solution. All right, so if there's no solution to this part, we don't have to worry about 5 over sine x. So there's no solution to this, so there's no equality condition going on here. And again, if you just think of the shapes of the secant functions and just function, the range of a secant function is greater than 1, anything greater than 1, anything less than -1. So there's no way these could ever be equal to each other if these constants are different. So there's no solution. Therefore, we actually have a strict inequality here, if you care. But what we've found is that 12 is an upper bound using Cauchy Schwarz and just a little bit of trigonometry. I don't think it's particularly sharp. It's sharper than the 15 that we did at the beginning. You'd have to look at the graph of this, I guess, or know more about inequalities than I do. But we have found an upper bound, not a least upper bound. Not, you know, and let me write that down. We have not found, not what they call an LUB, least upper bound. We have found an upper bound for sure, but I've done nothing that would prove that it is the least upper bound. Thank you for viewing.